Okay, so welcome everyone to this session of the Zoom Algebraic Geometry Seminar. So our speaker today is Eva Elduque, and she will speak on Eigenspace Decomposition of mixed Hodge structures on Alexander models.
All right, well, thanks for inviting me. This is joint work with Eva, who's also at my institution in Madrid. So, okay, here's an outline of the talk. So first, I'm gonna start with the setup. So I'll talk about what Alexander modules are, as well as mixed Hodge structures, so that we know what I'm gonna be talking about. Then in the second part, I'll review a mixed Hodge structure that in joint work with Christian Geske, Moises Herradon-Cueto, Laurencio Maxim, and Botan Wang, we put on these Alexander modules that I'll be defining. And we'll also explore some of the relationship that it has with other mixed Hodge structures in the literature. And the most important one is gonna be the one with the mixed Hodge structure on the Milnor fiber. And so we'll explore the analogy between the mixed Hodge structure on the Milnor fiber, a cohomology of the Milnor fiber, and our mixed Hodge structure. And that's going to be the more recent work that I'm going to be talking about on part 3. And part 4 is just examples that are well suited for computations. Also, since Zoom, I can't see you, please unmute yourself and ask questions at any point. Okay, setup. So what are Alexander modules? We're gonna start with a smooth connected complex algebraic variety U that has an algebraic morphism to C star. And we're gonna impose that it will induce an epimorphism on fundamental groups. Okay, so we're gonna construct an infinite cyclic cover from this U and this F as follows. So, okay, we have the exponential map, which is the universal cover of C star. And we're gonna pull it back through F. And whatever we get on this upper left-hand corner is a covering space, this time of U, and the deck group of this covering space is the same one as the deck group of the exponential map, which is just the integers. So by infinite cyclic cover, I just mean a covering space such that the deck group is the integers. And well, the first problem that we encounter is that the exponential map is not an algebraic map. It's not a polynomial, so we have left the world of algebraic geometry by doing this diagram. I mean, we haven't left dramatically because this infinite cyclic covering space that we're going to be focusing on is a complex analytic manifold that's just not algebraic in general. Okay, so this UF is our main object. So we're gonna fix a field, either the rational numbers, the reals, or the complex numbers, and the Laurent polynomial ring with coefficients over that field. And here we have a sheaf, which is not gonna be super important for the purposes of this talk, because I've tried that it doesn't appear much. But let's talk about it a little bit. Okay, so if you take the constant sheaf on this infinite cyclic cover and you do the proper push forward and you push it forward to U, you get a rank 1 locally constant sheaf. And if you look at the stock, you can see that it's isomorphic to the Laurent polynomial ring. So just the sheaf on U that we like, that is related to this infinite cyclic cover. And in fact, it is very much related, as we're gonna see. So here's the definition of Alexander modules. In homology, the jth Alexander module is just the jth homology of V-space, which one can see that is canonically isomorphic to the jth homology of U with coefficients over this sheaf, local system. So, and this isomorphism is as modules over the Laurent polynomial ring. So T acts here by generator of the deck transformation group, and also here as well. And so maybe this description with the local system, it's easier to see using this description that this is going to be a finitely generated module over the Laurent polynomial ring. Okay, so in algebraic geometry, we tend to care about cohomology and sheaf cohomology, not homology. So let me justify why I'm gonna do this whole talk in homology. So why not cohomology? Well, the thing is, we've left algebraic geometry, and now this thing is a finitely generated module over the Laurent polynomial ring, but the Laurent polynomial ring is a PID, so it has a decomposition into its free part and its torsion part. And if the free part is non-trivial, then, well, as a vector space, the jth Alexander module, so the homology of this covering space, has infinite dimension, but it's countable, so manageable. But this thing where if you take the dual of a direct sum, it becomes a direct product, the cohomology has uncountable dimension as a vector space, so it's not even a finitely generated R module. And we like that structure for modules over a PID, right? When they're finitely generated. So this is why we're going to be focusing on homology, because it's just smaller. It's a more manageable object. Okay. So this is the main object of the talk. Let me motivate why I care about this. So an important example is that of affine hypersurface complements. So if you start with a polynomial, and you look at the hypersurface that it defines on affine space, I work over the complex numbers always. Then you can look at its complement. And Lipkover was the first person to take these notions of Alexander modules from knot theory to singularities and to algebraic geometry. And he noticed that the Alexander modules constructed with this U and this F carry information about the type and position of singularities of the hypersurface that you started with. So even though you study a smooth manifold, it has to do with studying the singularities of the zeros of F. And so here's a motivating example, that of Zariski's sextics. So if you have a curve in C2, and the only thing you know about it is that it's an irreducible sextic, which only has 6 singularities and there's 6 cusps. Then if you look at this infinite cyclic cover and do the first Alexander module, it turns out that the first Alexander module is this thing, if the cusps all lie on a conic. But of course, 6 points in general position are not on a conic. And if they're in general position, the Alexander module is 0. So we can think of these Alexander modules as sort of detecting how the hypersurface is embedded into affine space, or giving us information about that and its singularities. Okay, so that's all I wanted to say about defining Alexander modules, and now I have to define, well, give the basic definitions of Hodge theory. Let's do that. Okay, so a Hodge structure, or a pure Hodge structure of a certain weight, is something that a finite dimensional vector space can have, and it's given by the following data. So you have to have a decreasing filtration that's defined on the complexified vector space. And the condition that it has to satisfy this filtration in order to be called a Hodge filtration is that, okay, if you take indices P and Q that add up to m+1, where m is the weight, then the complexified vector space is just the direct sum of the P part and the complex conjugate of the Q part. Okay, so if one has a filtration that satisfies those two conditions, then what one gets is a direct sum decomposition, which is what I want you to take away from this Hodge structure. It's a way to get a nice direct sum decomposition, where the parts are given by, okay, they're the PQ part. And so you take P and Q that add up to M, which is the weight. And the PQ part is the P part of the filtration intersect with the complex conjugate of the Q part. And so here you can see that VPQ is going to be the complex conjugate of VQP. So in this direct sum decomposition over here, one can sort of pair up the sum ends into vector spaces that are complex conjugate to one another. So it's a strong extra structure. And why do we care about Hodge structures? How did this definition came to be? Well, if you use a smooth compact algebraic variety, then the cohomology, the jth cohomology has a canonical and functorial Hodge structure of weight J. Also, if U is a compact Taylor manifold. And there is a notion of dual Hodge structure, so one can also endow the homology with a Hodge structure. It will just have weight minus J. And so the first consequence is that, okay, if J is odd, then the jth Betti number of a smooth compact algebraic variety has to be even, because you can pair up the summands in this Hodge decomposition into two summands that have the same dimension because they're complex conjugate to one another. So, you know, it puts a strong restriction on which Betti numbers can appear as Betti numbers of smooth compact algebraic varieties. And okay, so a Hodge structure is a nice way to get a direct sum decomposition in a finite dimensional vector space. What is a mixed Hodge structure? Sorry. So, okay, a mixed Hodge structure is something that's also defined in a finite dimensional vector space. And it is given this time by two filtrations. One is an increasing filtration that we call the weight filtration. The other one is the Hodge filtration, which is defined in the complexified vector space as before. And the way that these two have to interact in order for us to have what's called a mixed Hodge structure is that, okay, with your weight filtration, you break up your space into successive quotients as follows. And if you look at this mth graded piece, then the same Hodge filtration, the one you have defined on the whole complexified vector space, induces a Hodge structure of weight m in these successive quotients. So, you know, it's like you have a weight filtration that breaks up your vector space into successive quotients, and you have different Hodge structures from the previous slide on each of these parts, and they have different weights. Okay, so this is a generalization of the concept of Hodge structure that the Lean came up with, because if U is a complex algebraic variety, but it's not necessarily compact or not necessarily smooth, then the cohomology no longer has a canonical and functorial Hodge structure, but it does have a canonical and functorial mixed Hodge structure. And so for us, the problem is that we're looking at the jth Alexander module, which was this thing, which is not a finite dimensional vector space, because it was a finitely generated module over the Laurent polynomial ring. But if the free part wasn't trivial, then this is infinite dimensional. So mixed Hodge structures are not even defined for infinite dimensional vector spaces in principle. So the solution we came up with is, okay, the problem is going to be the free part, because that's the finite dimensional part. But if you look at the torsion, then, well, this is the biggest submodule which is a finite dimensional vector space. And we want the module structure to remain in whatever we study, because if we remember, the way T acts on this thing is by a generator of the deck transformation group. So if we really care about the infinite cyclic cover as a cover, not just a space, then looking at the torsion is a, the natural solution, let's say. Okay, so from now on, we look at the torsion of the Alexander modules. And let's review this mixed structure that we put there. Let me recap all the notation that we've been using. So, okay, we started with a smooth connected complex algebraic variety that had a map to C star, which induced an epimorphism on fundamental groups. I don't think I've said it, but the reason we want this to be an epimorphism is just that this UF is connected. But it's not super important, I guess. And then we constructed the pullback diagram from the exponential in F, and whatever we got here was an infinite cyclic cover, which is what we studied. I'm gonna fix rational coefficients just because it's the most general statement that I can give. And so the theorem that we had in a very long and technical paper that's gonna appear as a memoir of the AMS, joined with Geske, Cueto, Maxim, and Wang, is that, yes, we can endow these things with a canonical and functorial mixed structure. So, okay, Alexander modules have mixed structures like this. And one can think of this in different ways. So the Leans theory pertains to algebraic manifolds. So this sort of extends it to certain non-algebraic manifolds. I mean, very special non-algebraic manifolds that arise from pullbacks like this, but non-algebraic nonetheless. And this whole thing with pulling back the exponential, if you've seen the limit mixed structure before or nearby cycles or something like that, it might look familiar. This is just like the global setting. So in our paper, we actually prove a relationship between the limit mixed structure when F is proper and these things on Alexander modules. But we're not going to focus on that today. It's just in case it's familiar to any of you. But okay, it's the interpretation. So let's talk a little bit more about this mixed structure. First of all, why would we even care that we have a mixed structure on Alexander modules? So I'm just gonna
have a little question.
Yeah.
So what functorial means for diagrams?
I mean, like, if I have two algebraic varieties with two maps to C star and an algebraic morphism between them, then whatever infinite cyclic covers you have on top.
Okay, thanks.
Like that. Yes, good question. Okay, so just an application to motivate why we would care about having Hodge theory. So from how we constructed the mixed structure, we could deduce the following, which is just a bound on the Jordan blocks of the action of T on the torsion part of Alexander modules. So again, T acts as a generator of deck transformations, so it has a geometric meaning. And the Jordan blocks have this bound, I mean, whatever, a number. The most important case is probably when you make J equal to 1 here, because this becomes 1. So it means that the action of T on the complex Alexander module is diagonalizable. So over Q, it's a semi-simple module over the Laurent polynomial ring. And so this statement has nothing to do with Hodge theory. It's just that you need the Hodge theory to prove it. And I just wanted to mention it, even though it's not related to the rest of the talk, because to sort of motivate doing Hodge theory here, because it's quite surprising in hindsight. So when we proved this, we didn't know that this was gonna be the case, but this first Alexander module, its torsion part, is not semi-simple if you relax the two assumptions that we have when we constructed Alexander modules. So after this was posted on the archive, Lipgover came up with an Alexander module, a first Alexander module whose torsion part was not semi-simple, but it's just that he didn't construct it from an algebraic map from U to C star. He just did the construction from a continuous map from U to S1. And the other assumption we had is that U was smooth. And if you relax that in a follow-up paper, we found an example where this is not semi-simple. So having the mixed Hodge structure really, and the properties that it has in the smooth case really can tell these kind of things apart. Okay. Let's keep going then.
So if U is not smooth, you don't get a mixed Hodge structure, or you do get one, but the weights go up and down?
Good question. So we don't get one in this paper that I'm talking about. We do get one in this one. The problem is the weights, as you suggest. But the one we get here in this other paper, we use different techniques. So we use mixed Hodge modules, whereas in this one we don't. And it's not clear that the one we get here recovers the other one, probably not. And it seems less canonical, which is weird. But you do have a Hodge structure. It's just some of the nice properties that I'm gonna say we don't know for that Hodge structure in the non-smooth case, like the properties that come from geometry.
Thanks.
Okay. So here's the proposition of Boulud, Liu, and Wang that says that, okay, this has nothing to do with Hodge theory. It's just for Alexander modules constructed in the way that I did. There exists an n such that t to the n minus 1 acts nilpotently on the torsion part of Alexander modules. Another way of saying this is that the eigenvalues of the action of t on the torsion part of Alexander modules are nth roots of unity. And the reason I wanted to recall this result is because this particular value of n turns out to be very important in the construction of the mixed Hodge structure and in the fact that it exists. So let me just briefly and very hand-wavily say how we constructed the mixed Hodge structure. So we modified whatever Deligne did with techniques called mixed Hodge complexes of sheaves. But Deligne endowed the cohomology of complex algebraic varieties with a mixed Hodge structure. So whatever he did to endow a certain n-fold cover of U with a mixed Hodge structure, we sort of twist that in some ways to get our mixed Hodge structure here. But so you sort of have to pass to a finite cover of U, and the finite cover of U that you need is given by this n, which in fact is hard to compute in practice, the value of n, but we know it exists. And so for a mixed Hodge structure, I said that you need a weight filtration and a Hodge filtration. And well, the way we did it is we defined those filtrations at the level of complexes of sheaves that lived on a good compactification of UN. So that seems more algebraic geometry than looking at homologies of covering spaces that are not even algebraic, but this is where these things arise. Okay. So the geometric properties of the mixed Hodge structure on Alexander modules, that we don't have in the non-smooth case, or at least we don't know that we do. The relationship with the Leans mixed structure is okay. The whole point of this was to study an infinite cyclic cover that was given by this map pi. And so in here, we have the Leans mixed structure. In here, we have our mixed structures. And, you know, this map induces a morphism in homology. So we would want the two to be related through this map. And yes, so this is a morphism of mixed structures. So what that means is it takes the wave filtration to the wave filtration, the Hodge filtration to the Hodge filtration. Okay. And so the main relationship that we're gonna explore from now on is the relationship with the Miller fiber. So let me explain. In the cases where we have a global Miller fiber, we're in the following setting. So say you have a weighted homogeneous polynomial, and you look at the complement of the hypersurface that it defines. Now F induces a map from U to C star, like we were having, but this time it's a fibration, the Miller fibration. And you can just take a fiber, and that's the Miller fiber. So in this setting, the Miller fiber and Alexander modules are related because, okay, you have the inclusion from the fiber into U, and it lives to a homotopy equivalence from the Miller fiber to the infinite cyclic cover that we cared about. And so, you know, homotopy equivalences induce isomorphism and homology, so we would want it to preserve the Hodge structure. And yes, so the two mixed Hodge structures are isomorphic. Our mixed Hodge structure and the Leans on the global Miller fiber. So in the cases where Alexander modules are isomorphic to Miller fibers, the Hodge theory that we developed is the same. And from now on, I want to explore the analogy because these things, Alexander modules, are not always generalizations of Miller fibers, because you can have Miller fibers in the local setting and then they're separate things. But the Miller fiber has been extensively studied. So I just want to know what's true in the Miller fiber setting that could potentially hold true in our setting, with this vague analogy that I'm given that becomes an actual isomorphism in the case where they coincide. So let me do that. So, okay. With the analogy that I want to convey is, okay, in Alexander modules, that's an infinite cyclic covering space. You have the deck transformation group, and that is what multiplication by T exemplifies. But in the Miller fiber setting, what you have is monodromy, and that's what T does in the Miller fiber setting. So, okay, what is true for the monodromy in the local Miller fiber setting? Well, okay, we have a Jordan-Chevrolet decomposition in that, okay, this is a linear algebra fact. So every invertible linear map between finite dimensional vector spaces can be uniquely expressed as the product of two different linear maps, where one is semi-simple, one is unipotent, and they commute. Why do I bring this up? Because T does not respect Hodge theory in the mixed Hodge structure on the local Miller fiber, but the semi-simple part of the monodromy, so the semi-simple part of T, does induce a mixed Hodge structure isomorphism. And so several people contributed to this. The first person to do the proof, I think, in the full generality that I needed is that I'm talking about is Navarro-Aznar, but I think Kulikov also did some cases. Saito recovered it with his theory afterwards. So many people contributed to this result, but to me, this is a remarkable result because, well, Steenbrink defined the spectrum of a hypersurface singularity, and that definition needs the fact that the semi-simple part of the monodromy induces a mixed structure on isomorphism on cohomology. And the spectrum is an invariant that I find very fascinating because it's related to other invariants that are defined in very different ways, like Bernstein-Sato polynomials, multiplier ideals. So to me, it's quite amazing that things that are defined Hodge theoretically like this actually have a counterpart in things that don't use Hodge theory at all and that come from different contexts. But if we want to continue the analogy, the natural question is, well, what about in our case? Is the semi-simple part of the monodromy a mixed structure isomorphism? Hopefully it is. I mean, I don't know if there'll be like a global analog of the spectrum that's worth studying, but continuing with the analogy is the natural question to ask. And so that's what we're gonna see. This question. So yes, yes it does. The semi-simple part of the T action is a mixed structure isomorphism also in the setting of Alexander modules with the mixed structure that we define. So let me sort of give a hand-wavy idea of how one goes about proving such a thing. So here's the idea. I said that the way that we define the Hodge structure here, the mixed Hodge structure, was, okay, the filtrations were defined at the level of complexes of sheaves, and they lived on a good compactification of a certain finite cover of U. And so you have to sort of go to where the filtrations were defined and find a morphism that represents the semi-simple part of the T action. And so first you look at, okay, what would play the role of T? And that's not so bad because, well, T has a geometric meaning. It acts on UF by a generator of the deck group, but this UN is an n-full cover of U, so you can also think of T as acting as a generator of the deck group of this finite cover that we have to go through. And there's a way to extend that to whatever sheaves we want to a good compactification of the cover. Again, I'm being hand-wavy. So now that we have a candidate at the level of complexes of sheaves that's gonna play the role of T, and by the uniqueness of the Jordan-Chatelet decomposition, we can find our candidate for the semi-simple part of the T action, but at the level of complexes of sheaves. And once we have that, since the filtrations were defined at the level of complexes of sheaves, you just check that it takes filtration to filtration, and that's how you prove that this thing is a mixed structure morphism. Again, hand-wavy. But I guess what I wanted to get at is the corollary of this, which is the eigenspace decomposition. So, okay, if you have a polynomial and you denote by the subscript G the kernel of G evaluated at the semi-simple part of T. So again, the semi-simple part is a mixed structure morphism. So if you take powers of it, then that's also a mixed structure morphism, and linear combinations of powers, also a mixed structure morphism. So the kernel of a mixed structure morphism is a mixed structure. So these things are naturally sub-mixed structures of just the torsion part of Alexander modules. And the corollary that we get is, okay, the direct sum decomposition that you have into generalized eigenspaces of the action of T on the torsion part of Alexander modules, you have a direct sum decomposition to generalized eigenspaces because we know that from linear algebra. But the corollary is not saying that the direct sum decomposition exists. We know that it does as vector spaces. Is that it's a direct sum decomposition as mixed structures. And so this mixed structure, the one that we created, is maybe simpler than we thought because at least it's a direct sum of other smaller ones. So I guess the natural question here is, okay, you've simplified your problem of studying mixed structures and Alexander modules into, well, you know, you have a direct sum decomposition, so you can study the summons. Can we compute any of these summons, the mixed structures here? So that's what we're gonna be talking about next. And so what is a mixed structure summon that always appears? Well, the sum is over the reducible monic factors of x to the n minus 1. So x minus 1 is an irreducible monic factor of x to the n minus 1. So we're gonna study the eigenspace of eigenvalue 1, because it's always a summon. Okay, so let's focus on that one. Why do I think that this eigenspace is important? I'm gonna give 2 reasons, and they sort of contradict each other, but I think it's gonna make sense, so bear with me. Okay, so the torsion part of the jth Alexander module is always isomorphic as mixed structure as the to the generalized eigenspace of eigenvalue 1 of a different torsion part of a different Alexander module. Don't worry about the notation, but I guess what I'm saying is that we don't lose generality by studying only the one eigenspace. But that also tells me that I'm not going to be able to compute anything about this eigenspace in general, right? Because I can't say things in full generality. So, okay, plus we don't lose generality, con, we don't lose generality. But speaking of the con, if you know U very well, this smooth algebraic variety that you started from, then you have more chances of being able to compute this mixed structure summon, because we proved a result on our paper that I think has the potential of helping implement the computation of these things, which is that you can construct this mixed structure on this summons without having to pass through a finite cover. So you sort of just remember that in the whole torsion part of Alexander module, we had to modify the Leans construction on a certain finite cover UN, but now we can just modify the Leans construction on U and get our mixed structure. And so hopefully, if the mixed structure is easy on, well, the Leans mixed structure on U, hopefully the mixed structure and the mixed structure summon that we care about, the eigenspace of eigenvalue 1, will be computable. So I guess the last part of the talk is just talking about what are good candidates for you that actually allow me to give you an example of this mixed structure to actually compute it. So we're gonna do that now. Okay. So that's the last part, formal varieties. Okay. This slide is quite technical, but let's try to focus on the important parts. So, definition of something being formal is for real manifolds. So a real manifold is formal if the global sections of its real de Rham complex can be joined through a zigzag of quasi-isomorphisms of CDEAs to some homology algebra. Okay. What I mean is, from the point of view, if you care about derived categories, a formal manifold is something whose de Rham complex is a complex with a zero differential. This through a zigzag of quasi-isomorphisms is what I mean. Okay. And so one can generalize this definition if instead of imposing that the relationship with a complex with zero differential be through quasi-isomorphisms, if you impose that they be through quasi-isomorphisms, but only up to a point. So this is what I mean. If you take an integer or infinity, and our quasi-isomorphism is, okay, a morphism between chain complexes. A quasi-isomorphism would induce isomorphisms in cohomology in all degrees, but our quasi-isomorphism induces isomorphisms only up to a certain degree, and then it's injective in the following step. But for degrees bigger than r plus 2, then you have no control, or you don't care, I guess. And so an R formal manifold is, well, if the global section of the real de Rham complex is essentially a complex with zero differential up to a certain point. The actual definition is not going to be important for what I'm about to say, but I guess the takeaway is that for some reason, complex algebraic varieties which satisfy these definitions, which is a condition on the real de Rham complex, have nice properties for the purposes that I want to use them for. Okay. There's, oh, here, okay, if infinity, then we recover the previous definition. There's this purity implies formality result that is very nice by Dupont, which says, okay, if we have a smooth complex algebraic variety and the Lean's mixed hash structure is nice up to a point. So, okay, either for all degrees up to a point r plus 1, the mixed hash structure is indeed pure, so not just mixed. So it's a hot structure of weight j, or up to a point, it's a hot structure of weight 2j. If any of these conditions hold, which is, Hodge theoretic conditions, then the smooth complex algebraic variety as a real manifold is formal, or R formal. Okay. For the purposes of how we're doing Hodge theory, I want to emphasize the following. So the first cohomology of C star is a pure Hodge structure of weight 2. And so since we constructed this whole thing with a map F from U to C star, then you can pull back this mixed Hodge structure to here. And so in the cases that we're going to be looking at, the ones that have algebraic morphisms to C star, the first cohomology of the variety actually has a sub-Mixed structure of weight 2. So we can only have case 2. Like, if you're in a setting like in case 1, you're never going to have an algebraic map to C star. So we're only interested in varieties that satisfy this condition. And he also noticed that in case you have this case 2, you could also say more. It's not that the mixed structures are pure of weight 2j, it's something stronger. They're pure of type jj. So I'm not going to define what this pure of type jj means, but basically, okay, being pure of weight 2j only tells you that it's a pure hot structure, so you have the direct sum decomposition. Being pure of type jj tells you what the direct sum decomposition is. So this is stronger. But it just so happens that for algebraic varieties, this weaker condition implies the stronger one. Okay. So in homology, you always dualize and it will also be pure, just with negative signs. So the main point here. Formality implies semi-simplicity in eigenvalue 1. Let's see what I mean. Okay, this is a proposition that Boudou Wang proved in the formal case, and we generalized it to our formal, although the generalization is not hard, it follows the same steps. Okay, then the generalized eigenspace that we are looking at, the one eigenspace, will be semi-simple if U is formal. And if it's our formal, well, only up to a point. And the main idea is that, okay, this had to do with the homology of a certain local system that you can resolve via the Ram complex that has to do with the Ram complex that is involved in the definition of our formal. So the two notions tied together through the fact that they're both related by forms, by differential forms. Okay, then we have another lemma, which is not hard to prove, which is, okay, in the case where we have semi-simplicity of this, which if the manifold is formal, we do, then the restriction of the infinite cyclic covering map in cohomology, in homology, but restricted to one eigenspace, it's injective. So we already knew that this was a morphism of mixed structures. And now what this is saying is that this is a sub-mixed structure of this. Which is great, because if we can control the mixed structure here, which is the Leans mixed structure, then, well, the mixed structure on our eigenspace will be just something smaller that lives within it. And so the summary is that, okay, if the jth cohomology, this is the Leans mixed structure, is pure of type JJ up to a point, then Dupont's theorem tells me that U is formal, so this is semi-simple. So this is a sub-mixed structure of this. But if the cohomology was pure of type JJ, the homology is pure of type -J, and any sub-mixed structure of a thing of type -J is also of type -J. So it sort of all ties together. And as a summary, for these varieties, which have a very, very nice mixed structure, then if you construct the Alexander modules, the one eigenspace, I know the direct sum decomposition. Okay, well, this is kind of dry as stated because I didn't actually give you an example, I just said conditions. But here we have examples. So if U is an affine hyperplane arrangement complement or a toric arrangement complement, then the hypotheses that I have is satisfied. So the jth cohomology, the mixed hot structure there is actually a hot structure of type JJ. And so I can compute my mixed hot structure on the one eigenspace. And so I just wanted to end with the example of hyperplane arrangement complements and what we know in that case. So we know a little bit more. So again, if you have a central hyperplane arrangement complement, all of the hyperplanes go through the origin, then that's given the whole arrangement by the zeros of a homogeneous polynomial. So you can look at the global Miller fiber and I said that whatever mixed hot structure we have there coincides with our mixed hot structure on Alexander modules. But the mixed hot structure on the Milner fiber has been extensively studied before us. So I guess I'm interested only in the non-central case just because it hadn't been studied. So okay, if I have a hyperplane arrangement where the hyperplanes are given by the zeros of a reduced polynomial, and I look at a defining polynomial of the whole thing. So I just take positive powers of each of the polynomials defining each of the hyperplanes and just multiply them all together. Then I look at the complement. And I know because of work in my thesis that the jth Alexander module is actually torsion in this case. And the reason I wanted to finish with this example is because we can actually talk about the mixed hot structure on cohomology, which if you do Hodge theory, the whole homology business was weird up to now. But because there's no free part, I can dualize and I still have a manageable object. So I'll just talk about the mixed hot structure on cohomology. And okay, we have our theorem. Okay, this is the direct sum decomposition into generalized eigenspaces. This is the generalized eigenspace that we've been talking about. And this is the direct sum of the other ones for other eigenvalues that are not one. And so this mixed hot structure isomorphism, we saw a while back that it exists, but what about the pieces? So this much I've said. The one eigenspace will be pure of type JJ, and that completely determines the mixed hot structure if you know the dimension of the space. But I know the dimension of the space. It's an alternating sum of Betty numbers of the complement. And I know that that is the Betty numbers of a hyperplane arrangement complement only depend on the combinatorial data of the complement. So this mixed hot structure I can compute and it's combinatorial. Okay, what about this one? Obviously, I don't have much information. All I can say is that if f is reduced, so all of these exponents are 1, then I know that this is pure of weight 1. But if j is equal to 1, but I don't know what happens for other values of j. I don't. And so this much is known in the central case, like I said, because we have a global Miller fiber. And these are results of Budurdin, Casaito, Papadima. And they know a bit more for this summon. They know that it just doesn't have weight 2j. All the weights that appear are smaller. And that we can't prove or disprove so far. Maybe there's a generalization, but much of what is known in this case, we know generalizes to the non-central case. And yeah, that's all I wanted to say. Thank you very much.
Thank you very much. So we have time for questions. So if nobody says something, I have at least one question. So if you take a homogeneous polynomial, you recover the limit mixed Hodge structure for the Miller fiber.
Isn't that the one? I think that coincides with the Lean's mixed Hodge structure. So
You can
yeah.
do two things. That's it. That I don't remember. So you have the Lean construction.
I asked someone and they told me yes.
But the question is different. So suppose you have a polynomial, not necessarily homogeneous, and assume that the zero fiber is a typical fiber. So the singularities are away from the zero fiber. And now you extract the zero fiber from Cn, and you have a mapping from that Cn to C star. And that mapping seems to satisfy the surjectivity. That is the only condition. So what is the meaning? What is the meaning of your invariant in that case? Because you have singularities away, but somehow, I don't know if it seems that your invariant takes care, special care of the singularity at zero or at infinity. But you may have many singularities in the affine part. So do you have an intuition of what can it say?
Yes. So okay. Let's think in cohomology because maybe it's easier. The inclusion of a typical fiber, not the one that you're removing, but in a neighborhood.
Well, I am removing a typical fiber.
Yeah, but the nearby ones are also going to be typical, right? That inclusion is going to be maybe I should write. Let me annotate. I think I can annotate. Or maybe I can't. I thought. Oh, yes, here. Okay. So you're saying, okay, I have you, and I have my map to crap. Okay. Sorry, it's bugging. To C star given by F. And so the fiber that I've removed is typical.
Yes.
And so, okay, here I have a typical fiber and I have the inclusion into U that also lifts to an inclusion of my thing. And so in homology, but I haven't used homological notation, so let me just translate that in my head. In homology, what I'm going to have is a and this map is a surjection. If only if this is semi-simple. No, sorry, it's always a surjection, I think, but it's only a mixed Hodge structure morphism if it's semi-simple. So I feel like if we're removing a typical fiber, well, I think maybe potentially things could go wrong away from a 2 or whatever that would make that thing not semi-simple. But in principle, I think you would only, if you're only looking at a tube, then in homology, you would have injections, and this would be injected into here. So if this was nice, it would just be a sub thing, and it wouldn't maybe carry a lot of information that maybe the fiber itself carries. But yeah, I don't know if semi-simplicity could be affected by the other singular fibers that you have away from the origin. And so if there would be a relationship, no. So Moises is saying in the chat, wouldn't the T action be trivial in that case? It would be trivial here in the fiber. But I don't think it'd be trivial.
Can you use your invariant for measuring the singularities that are away from zero?
I guess, I mean, if there were none, I could tell if it was a vibration, because this would be an isomorphism, and if it's not, then, but yeah, that's the thing with these things, that, you know, you have very little control about the things that happen away from the origin, but they also.
So there is a contribution in the chat.
Sorry, what?
There is a contribution in the chat. So it says wouldn't.
Yeah, that's what I answered. So the action of T here, it would be semi-simple because, okay, you locally you have a T action because of the monodromy, because it's the identity, but here I don't know what T is.
Yeah.
That's what, and we need this part to be semi-simple.
Yeah. I was.
Can I say something?
Yeah.
So
we showed that that's a rejection of modules.
Yeah.
So that the action is trivial on the Alexander module as well.
Oh, true that. Okay.
and you also you did this retraction argument that kind of answers the other question too. When you have like more singular points, it has the homotopy type of a wedge. So if you understood the singularities kind of make the kernel of the map bigger.
Yeah.
And
I feel like the more singularities you have outside, the smaller your Alexander module is gonna be.
Yeah, and so we showed that in that case, the map is a mixed structure morphism.
Yeah.
I see.
Yeah.
Thanks.
Sorry.
Any more questions? Okay, so thank you very much for your beautiful talk. So I'll stop recording and close the session.
Thank you.